And we are back. This is the second class period here on Friday, July 10th. This is chapter 21 we're starting, which is carbonyl additions, aldehydes and ketones. Now, we've already been doing that kind of thing with hydrides and Grignards, but now we're going to learn a different set of nucleophiles that give some very important products. And this will kind of begin the biomolecule part with imines and enamines that are very important reactions to keep straight. So we'll have some new nucleophiles here for aldehydes and ketones. Plus we'll do nomenclature of aldehydes and ketones, which we haven't done yet. So we finished chapter 20. We did a bunch of synthesis problems and some of the homework type problems. So that homework 5 is due tonight. Very good. Let's go up here on the overhead and see what we need to know for chapter 21. Like I said, it is nucleophilic additions here to aldehydes and ketones again, another chapter. But first we'll do some naming. And alkane is the parent to alkanal here for aldehydes. That's the abbreviated drawing for a functional group aldehyde. Aldehydes are always on the end. That's the C1 position. Ketones, the carbonyl can be in the middle there. And the main name there is alkanone. Alkane diols for dialdehydes, yeah, okay. Lowest number to the carbonyl, if it's a ketone, the ketone has precedence over the other groups like alkyls and halides, but not alcohols. Alcohols have priority there. Precedent, no, over alcohols. Yeah, you're right, okay. And alkenes and halides have lower priority. Formaldehyde, acetone, benzaldehyde, there'll be some other common names, and we'll get to that also. Properties, sp2 hybridized, of course, 120-degree bond angle there. The carbon is partially positive. It's a polar covalent bond. There's significant dipole moment. Can be a hydrogen bond acceptor, but not a donor. In general, if there's less than 5 carbons, they're water soluble. IR, the big carbonyl stretch there at 1730. I'll say a little on NMR maybe. There's a couple of unique things in the NMR about that. We'll look at a lot of examples here. We might visit the Hall of Fame and Hall of Shame again. We've already seen some applications of aldehydes and ketones there. We'll review the preparations of aldehydes and ketones, so we're being very thorough there. And now the reactions begin, right? So the carbonyl is electrophilic, and the nucleophiles coming in here, and that adds to the carbon of the carbonyl, of course. Nucleophiles can be charged, of course. We can form enolates of carbonyls if we use a strong hindered base. We'll see those type of reactions later. Here's our nucleophiles, hydrides, organometallic reagents, acid catalysis. We've already seen a lot of these reactions. We'll review some of those. But now we begin the new reactions, and I believe there are 6 of them. Sorry, I'll point these out as clearly as I can. So aldehydes and ketones with hydrogen cyanide form cyanohydrins. The cyanide is the nucleophile. You protonate the carbonyl, add the cyanide, and then you get the alcohol cyanide. That's called a cyanohydrin. It's an archaic term. It's really an alcohol cyanide at the geminal position. They're both on the same carbon, so we call them Gemini or twins, okay? You've heard of halohydrins before. Those are vicinal. We formed those in 351, so maybe we'll relate that to that. But very useful reaction. The cyanide group is actually reversible, even though it is a carbon-carbon bond that's formed. You can reverse that with strong base, but cyanohydrin, that's number 1. Number 2 is a Wittig reagent, and that is a German name, proper noun. That's the name of Georg Wittig. Don't pronounce it Wittig. That's improper in German. It's Wittig reagent. It's right here. It's a triphenylphosphonium salt at first, and then it forms the phosphorane, it's called. The phosphorane is the actual nucleophile that will add here to the aldehyde or ketone, and then eliminate the phosphorus oxide. The triphenylphosphine comes off as the phosphorus oxide and leaves behind an alkene. So this takes a carbonyl, aldehyde or ketone, to an alkene. And whatever's on the phosphorane, the Wittig reagent, is incorporated into the alkene. These 2 carbons here, whatever they are right there and there. This is the opposite of a reaction we covered in 351. What does it look like the reverse of? if you take an alkene and go back to a ketone or aldehyde, that's ozonolysis, right? So the Wittig reaction is sometimes called reverse ozonolysis. We're stitching back in a carbon, taking the oxygen off and giving an alkene back. Very useful reaction, forms alkenes. We won't talk about how to control the geometry. We'll just talk about how to put these type of molecules together and how to make the Wittig reagent. You make it from the halide, triphenylphosphine nucleophile. This is called the phosphonium salt. We have to add strong base to form the actual phosphorane nucleophile that then adds to the aldehyde or ketone. Of course, we'll go into the details here. Now, reactions 3 and 4 here, imines and enamines. Imines are formed from primary amines, nitrogen compounds that just have one alkyl group on it. So you see this is a primary amine, nitrogen, 2 hydrogens, and an amine. Lone pair there. This can add to an aldehyde or a ketone. And we are limited to aldehydes and ketones in this chapter. We're not talking about derivatives of carboxylic acids. We're not talking about amides or esters. They give different type of products with these. Acid chlorides, different types of products. We're just limited to aldehydes and ketones. When we form the tetrahedral intermediate here, there's no extra leaving group, okay? But here we can actually lose water and form what's called the imine, the carbon-nitrogen double bond species, from the primary amine. Now, if it's a secondary amine, we form what's called an enamine, okay? Very close, these two names, imine and enamine. Enamine, though, implies what? An alkene, right? So here's a carbon-carbon double bond on the side, and this is from a secondary amine. This will eliminate water on the side here. You can't eliminate water twice here on this. You see, you just have the one carbon group here on the primary amine. And this will fall out of the mechanism. When we go through the mechanisms here, you'll see why primary amines go to imines and secondary amines go to enamines. What about tertiary amines? You can have up to 3 groups on nitrogen, right? Oh, those are reversible and don't give imines or enamines. Okay, and that's because you got to have these hydrogens that need to be removed. You have 1 hydrogen to take off here from a secondary amine. Here you have 2 hydrogens to take off from a primary amine, which can give the imine, the carbon-nitrogen double bond. Anyway, those are very important reactions in biology as well. There's a lot of reactions like that that form different intermediates in metabolism and amino acids, and we'll use those type of reactions later on when we talk about metabolism. Okay, that's reactions 3 and 4. I told you there were 6, right? Okay, we can also have water as a nucleophile here with carbonyls. This is called a hydration reaction, forms geminal diols. Well, this is completely reversible. This is kind of a degenerate reaction. It doesn't really give a stable product. I like to go through the mechanism of this and talk about the different factors on the R groups, how that affects the equilibrium. This should be an equilibrium arrow here. And if you try to isolate a gem diol, normally it just goes right back to the ketone and liberates water, okay? And that's because of the carbonyl resonance and the entropy effect. It wants to lose an equivalent of water and get that extra entropy, that extra randomness, and go back to the carbonyl, okay? But there are some effects here. If it's an electronegative R group here, it can actually be stabilized toward the geminal diol. Now, if it's an alcohol nucleophile, the story is different here. If we go all the way and add 2 here, new alcohols onto a carbonyl, you see we can get 2 ether groups on this geminal carbon. Now that's called an acetal. Now this is a different thing altogether. These can form very well under acid catalysis, especially with small alcohols, methanol or ethanol, or they can happen intramolecular. We'll show you that too. These are often used as protecting groups for carbonyls and aldehydes, ketones, whatever. And like I said, cyclic forms, which are related to sugars. We'll see glucose, mannose, galactose, all the simple monosaccharides exist mainly as acetals. So here's the example. Graphically, you can see with a ketone, acetone, and a new alcohol, methanol or ethanol, forming the geminal diether. That's called an acetal. And we'll specify that. That's a new functional group for us. It's really 2 ethers. We see an ether over here and an ether right here. but the two together on a single carbon, it has to be geminal on the same carbon, that's called an acetal. So you see, if we break this back apart, you can see where the ketone would be formed, right? And then the two alcohols can come back off. You'll see from the mechanism how that works. And this is an example where you need to know the mechanism. So if we treat this acetal with water and strong acid catalysis, we can go back to the ketone or aldehyde with liberation of the alcohols. Now, if we've got an alcohol in the same molecule with an aldehyde or ketone, you see the alcohol, lone pair on oxygen, can function as a nucleophile, push the electrons over, transfer the proton. You see this forms what? A cyclic acetal. We call this a hemiacetal sometimes because it's got an ether and an alcohol on it. If it's got two ethers like this, that's the full acetal. And so we can add another alcohol, different type of alcohol here, and form a mixed acetal. This ether is from the intramolecular thing here. And here's an external alcohol functioning as a second ether to form that cyclic acetal. Like I said, this relates to sugar chemistry, and this is really the only reason why we're covering this. They can easily be formed in the presence of the alcohol, and then they can be reversed in the presence of the water going back. All right, let's look at aldehydes and ketones in general. Catch your attention there and show you some things we've already seen. Some of these, I think. Yeah, so here's the Hall of Fame. They're used for all sorts of applications here. Some are disease preventative things. Genistein comes out of soybeans. That actually has antibacterial and anti-cancer effects. Raspberry ketone, that's a flavorant in raspberries. Quinone, we'll see that was used as a developing agent in photography years ago. Not anymore. We don't do wet chemistry for photography. It's all electronic now. No, some artistic people still use wet chemistry for photography. Quinones are also an electron transport chain in biology, the last part of metabolism. Cortisone, the anti-inflammatory agent, right there. Maltol, the essence of malt, the flavorant, it comes out of sugar processing. Camphor, a very pungent smelling compound, essential oil, comes out of a number of plants. Muscone, here is the the male hormone for deer. Deer animals emit this material to attract females. Ninhydrin is a triketone, and right here is a gem hydrate on the central ketone right here. So you'll see that as a hydrate there, a diol on one carbon. If you eliminate water, you can put the other ketone there. Furfural phosphate pyridoxal phosphate is a cofactor in biochemistry. Citronal al is a mosquito repellent material. Here's glucose, blood sugar. You can see the aldehyde with a bunch of alcohols on it. The stereocenters are important there. It's actually 4 stereocenters. We'll have whole chapters on glucose, obviously, and sugars coming up later on. Formaldehyde, the embalming thing that covalently cross-links DNA and forms cross-links with a number of other amines in biological tissues and preserves them. It also kills bacteria. So you can preserve biological samples indefinitely there. Erythromycin, a lot of you have probably taken this drug here. It's an antibiotic. And there's the ketone right there. A couple sugars are attached. Cucumber aldehyde, cinnamaldehyde, probably heard of that one already. Yeah. If we have the fame, we got to put up with the shame, I guess. Acetaldehyde is the drunkenness effect. If you drink too much ethanol, the liver oxidizes to acetaldehyde, and then this forms imines and enamines with different amines in the body that then shuts down nerve transmissions. You lose muscle motor control and a lot of other things if acetaldehyde builds up in the body. Chloral, Mickey Finn knockout drops, or a date rape drug, certainly deserves to be in the Hall of Shame there. It's got 3 chlorines there. The chloral in the presence of water actually forms a stable hydrate. We'll look at that later. Dihydroepiandrosterone is a testosterone replacement drug that's often abused by weightlifters and other people there. Diacetyl is the flavorant in microwave popcorn. It has a buttery flavor. and it's two ketones there together. It is a toxic material in high concentration. In fact, there's a diagnosed disease. It's called popcorn lung. People who work in microwave popcorn factories where a lot of this flavoring is being added can develop a condition in their lungs similar to white lung disease in minors. So this is a recent disease that's come about. It actually cross-links with DNA and causes different morbidity effects in cells. Periplanone, we got a ketone there. That's a cockroach pheromone. Isohumulones in beer, fermented hops. You got a ketone there, and there. Helminth sporols, a toxic material in the hemlock tree. Two aldehydes, that doesn't look like a real toxic thing, but it can form cross-links with DNA because the aldehydes are electrophilic and it's the right shape that can interact there. Fructose, this is related to glucose, it just has the carbonyl shifted over. Why is fructose in the Hall of Shame? Well, it's metabolized a little bit differently than glucose. If you don't need the energy and you're drinking a lot of high fructose corn syrup drinks or foods, whatever, fructose is metabolized into fat much more quickly in the liver. It bypasses the first two steps of metabolism that we'll see later on. Formyldienolone is another one of these anabolic steroids that mimics testosterone that's abused. We've already seen this application of aldehydes and ketones. Let me remind you, here's the aldehyde from retinal is the common name for that. It's a retinal isomerase that switches it from the cis alkene to the trans alkene. And then in the eyeball, this gets an interaction with these proteins here. And here's the protein called opsin. Yeah, there's a primary amine. So here's the key reaction. Primary amine with an aldehyde, yeah, forms an imine. Well, it's acidic enough to be an iminium ion. This is the actual light harvesting chromophore in the eyeball. Rhodopsin, the whole thing, retinal and opsin. Rhodopsin is called the construct of it. Initially starts out Z upon activation with light. So here's a photon of light. Picosecond event can excite this molecular orbital to a higher excited state, which allows for rotation around that double bond to go to the E alkene right there. That's the more stable form, okay? It takes this isomerase to switch it over to the less stable cis form. And then the light harvesting effect occurs at different wavelengths of light. That allows you to differentiate different colors. That occurs in your brain. The optical nerve accepts the signal. This conformational change, a G-coupled protein. Maybe you've heard about some of those, but this gets hydrolyzed, and then the retinal is actually recycled. So this takes a little bit while. This takes seconds. And you've probably suffered from temporary blindness sometimes. If you've had an intense flash of light come into your eyes, you're blinded for a couple seconds, and that's the time needed to bring back all of your opsin to accept more photons into your light, into your eyeballs. There. Anyway, just focus on the key thing there. So I don't expect you to know all the details about light and the harvesting that goes on there, but here's an application where we need to know something about these functional groups, okay? The aldehyde to an iminium ion. Nomenclature, we'll get into that in a second. Here's my general chart. It's been on Learning Suite the whole time there. And you see we're doing aldehydes and ketones now. Alkanal, alkanones there. And yeah, they do have priority over alcohols. Before in 351, the top priority group was alcohol. We'll see at the end here, alkanoic acids or carboxylic acids is the top priority, okay? Fully oxidized, you could say, yeah. Esters, amides, yeah. And then if you need to use the others as a prefix name, you know, I've already talked about this. Alcohol is a hydroxy or an amino for a prefix name. And there's the aromatic ones you need to know. You've already learned some of those, I think. But here's the general rules all in one chart, which I think can be kind of helpful that way. All right, let's go to the sideboard, and we'll see a general application here. Well, a couple more recent molecules to talk about maybe. And I point out these molecules just to show how they relate to the things we're talking about here in chapter 21. So here's acetone peroxide acetal. This is an explosive material. You don't see any nitro groups here, but you see a lot of oxygens. Here's the peroxy link. That's why it's called peroxy. And why is it called an acetal? Well, there's carbon right here with two oxygens on it. Two ethers, you could say. Yeah, they're peroxy ethers, but But yeah, it's still part of an acetal. And why do we say acetone? Well, it's made from acetone. Acetone is available commercially, of course. Many of you have used it maybe for nail polish remover or solvent material. You can buy it at the drugstore or the hardware store, wherever. And then peroxide, well, it comes from hydrogen peroxide, and you can get 30% solutions of that too commercially. And if you react this with toilet bowl cleaner, which is HCl, that functions as a catalyst to form the acetal, you can form solutions of this, the acetone peroxyacetal. Now that, like I said, is a detonation hazard, similar to TNT. So they screen for this at the airports now. In fact, this is why you cannot take liquids on airplanes. This is the reason why. The media will never tell you why, but you're learning it now, okay? So this can be made, and this has been attempted by terrorists a couple times to get this through security, and then in the bathroom at the airport, make this stuff, and then try to build a bomb going on an airplane. Very scary stuff. Again, a shock hazard here. This can go to CO2 very quickly. Those are both gas molecules, and yeah, where do the hydrogens end up? Well, methane can also be formed here. And again, this is a solid liquid material. It's in water, but still detonation acid. These are both gas materials, and it's easily made there. This was not detectable until they went to mass spectrometry detection here at the airport. That's the puffer machine, and the molecular ion there they're looking for is 222. That's the magic ion. If that ion shows up in the puffer machine, you're hauled off to a separate room, and they check you very carefully to make sure you haven't been making any of that or having any of that. All right, what's this other molecule over here? We got Xanax. What's Xanax? You probably know that as a sedative material. It's, I think, the most prescribed drug nowadays, used to treat all sorts of anxiety and stress issues, used in the clinic. And it's also a prescription drug, I believe, and used there. It's in the benzodiazepine family of drugs. And why are we showing it in this section? Well, peroxyacetal there, we have the acetal, okay, and that functional group here. Are there some functional groups here that we're going to talk about? Well, this triazole is an aromatic heterocyclic compound. We could have talked about that in chapter, 19? But no, we're in 21 now. And what do you see right here? Yeah, that's an imine right there. In fact, that's how this triazole is actually formed there. There's a carbonyl here that can be made. And there's actually another imine, right here. There's a phenylamine right there. And that actually suggests how it's made, but the chloride has to be there for it to have its sedative activity. Anyway, you can look up Xanax and learn a little bit about that being a sedative material. All right, let's look at the reactions in general with aldehydes and ketones. And we've actually already done this, but I like to point this out here and show reactivity-wise, the simplest aldehyde, formaldehyde, is more reactive than general aldehydes. So higher reactivity we're talking about. And ketones are far less reactive. And why is that? Well, the carbonyl, you see, is partially positive, right? So that partial positive character comes from the resonance structure, right? If we push the electrons up there, we have the meaningful resonance structure here that has a plus charge right there. So as far as nucleophiles adding, they're going to go to that spot. Well, if we've got big alkyl groups here and here on a ketone, how does that affect the reactivity? Right, sterics will make it less reactive. And sterics just means the size, the bulk of that material will impede the attack, the trajectory of the attack of the nucleophile. There's another factor here, though, electronics. And if you have an alkyl group here, that's electron releasing by hyperconjugation, right? So the more alkyl groups you have here, and the more electron-rich groups you have here, that can make this more stable or more blocked as far as the nucleophile coming in. You already have this extra stability, okay? And the nucleophile is not as attracted to that. But if it's formaldehyde, you don't have those effects. Or an aldehyde here with just one alkyl group on it, sterically it's easier to get in there. And electronically, it depends on what those other groups are there. But if you've got an electron withdrawing group here on a ketone, whatever, withdrawing groups, you see, that will make this attack of a nucleophile even more attractive. Why? Because they're pulling electron density out of that even more, okay? And we'll see that with the hydrates here in a second, what goes on there. All right, let's, before we get into the specific reactions, let's do a little bit on nomenclature, naming, alkanal. And so we take the E off and add Al for an aldehyde. And so it depends on what the parent is. And make sure you count the carbon of the aldehyde as part of the parent here. So this is 1, 2, 3, 4, 5, 6. So this is hexane, right? It's the initial parent, so hexanal. Now, do we need a number 1 here to say where the aldehyde is? No, it's always number 1. Okay. So we got the position there. And notice the name hexane. We're not calling this pentane with 5 carbons here and then aldehyde. No, it's hexanal for the whole thing there. And, we can have branching and other groups there. So, we could ask you about some simple names like this one. What's the parent? 1, 2, 3, 4. So that's butanal. And it's the longest chain, right? That includes the aldehyde. And so, if you have some trouble with that, circle the whole thing. And then what else is on the parent? Well, this is the 1 position, 2, 3. 3, what do we have? 3 methyl. So 3 methyl butanal. And yeah, that's maybe about as complicated as it'll get here. We just want to give you enough to understand that. And what if we got an alkene and an aldehyde? Which one gets priority? Yeah, the aldehyde. And we number it 1, 2, 3, 4, 5, 6, 7. So this is heptane, but because we got the alkene, it's heptene al. Okay. And the al here means it's number 1, right? And so where does the alkene start? 1, 2, 4, 5, 6. So 6 heptene al, and the 6 refers to the alkene right there. Okay. So yeah, the parent is modified heavily here, right? And the E here instead of heptane, and then instead of the E here is al. Okay. Let's see, we can do dialdehydes too. Alkene, dial. Oh, maybe I didn't. Oh, okay. We'll show this one. Alkane, dial. And, there you have the whole parent and then the dial. So something like this. Could be what? 1, 2, 3, 4, 5. So it's pentane. Sorry, pentane. The whole thing, pentane dial. You don't need to number because it's on the 2 ends. And then here it's symmetric, but you number from the lowest possible thing. So 1, 2, 3. So it'd be 3, 3 dichloro. Okay. Anyway, that lets you name some harder ones. This could also be called glutaryl dial from glutaric acid, which is the 5-carbon dicarboxylic acid. But yeah, don't worry about that. Let's just, yeah, shouldn't have even gone into that. Okay. Cyclic aldehydes are a little bit different. Cyclic aldehydes are cycloalkane carbaldehyde. H there, carbaldehyde, cycloalkane carbaldehyde. So if we have cyclopentane, this would be cyclopentane carbaldehyde. So that's part of the whole thing, or carboxaldehyde, sometimes it's called. So yeah, you have to draw out the whole name for whatever this group is here. That refers to that part, and then carbaldehyde for that. That makes those a little more difficult. There are a lot of common names. The IUPAC name for that would be what? Ethanal, and from ethane. but that's called acetaldehyde. And it comes from acetic acid. You take off the IC and add aldehyde. Okay, so acetic acid or acetaldehyde. Okay, is that guy. And this one, we've already seen this one. This was from chapter 19, I believe. So what's that? Yeah, benzaldehyde. I won't draw the whole thing out, but benzaldehyde. You include that carbon of the aromatic now aldehyde. Benzaldehyde. Benz refers to actually 7 carbon species. Benzyl alcohol. You can't have phenylaldehyde. You could call that formyl benzene. The formyl group is a prefix name for an aldehyde. If you have a higher priority group there, like a carboxaldehyde or carboxylic acid, you can call that a formyl group as a prefix name. So it'd be like if you had a carboxylic acid down here, you'd call that what? Benzoic acid. And then at the 4 position, you have formyl. So this would be paraformyl benzoic acid. And yeah, I'm not gonna, give you a bunch of examples like that. So don't worry so much about that. Cinnamaldehyde. Probably seen this. The essence of cinnamon. Essential oil out of cinnamon. It's the flavorant, and cinnamon can be made synthetically. I'll show you how to do that later on. But cinnamaldehyde. I'm not even going to draw out the whole thing. Let's see. We could name this a different way, though. Let's see. What would be the parent here? This would be propanal, right? So, and at the 3 position, we have, what, a phenyl? Okay. Phenyl, and then propene, the aldehydes at the 1 position, 2 positions where the alkene starts, 3 positions where we have the phenyl group. Do we need anything else here? Yeah, this is trans, so actually we need E out here, right? So E, 3-phenyl, 2-propanal. Thank goodness for common names. This is cinnamaldehyde. Okay. Makes it a lot easier. Let's do ketones now. Ketones are similar, you can say. Instead of alkanal, of course, we have alkanone, where we've got the E coming off, and you add ONE. And it sounds like a ketone, right? So not too bad there. The key thing here, though, is you need to specify where the ketone is. So it can be anywhere in the chain here. If the carbonyl's on the end, though, that's an aldehyde, right? So it's got to be at least in the 2 position or moved over. So let's see what this parent is. 1, 2, 3, 4, 5, 6. So it's hexane, hexanone. And let's see, where is the ketone numbering in? At the 2 position it starts. So that's 2-hexanone. And I think you can draw 3-hexanone. It would be over here. Is there a 4-hexanone? No, that would be the same as 3-hexanone. Is there a 5-hexanone? No, that would be the same as 2-hexanone. So keep track of the name, at least to help you with the structure there. I think that's enough to let you be aware of. How about a little bit more complicated one? How about a couple of halides on here? Here we got a chlorofluoroketone of some kind. We start with the parent, the longest chain, 1, 2, 3, 4, 5, 6, 7. So this is heptanone. And where is the ketone? 1, 2, 3, or 1, 2, 3, 4, 5. Well, 1, 2, 3. So 3-heptanone. And then what else do we have? We have 1 fluoro and then 4 chloro. And we just alphabetize that, right? So we have 4 chloro and 1 fluoro, alphabetizing, and heptanone. Is that it for that name? There's another thing we need to worry about there, and that's the stereocenter, right? I think I've drawn this with this coming out. The hydrogen in the back of the U2. Yeah, that is a stereocenter. It's specifying the one thing there. So what is that? Let's see. Top priority would be what? Oh, chloride. Then the carbon with 2 bonds to oxygen. Then that. And then the fourth one's in the back already. So yeah, what is that? That's R. R, 4 chloro, 1 fluoro, 3 heptanone would be your name there. Let's see, another way to name ketones is to call them alkyl-alkyl ketone. This is the IUPAC way, alkanone, or alkyl ketone. And this lets you say, well, whatever we've got on the side of the carbonyl group, we're just going to call it a ketone. Okay, so here we have an ethyl group and a propyl group on the ketone. So the systematic name would be what? To call this 3-hexanone. But you can see here you've got an ethyl group and a propyl group. And so how do we use that to name it as an alkyl-alkyl ketone? Well, we alphabetize them. We say ethyl comes first in the alphabet, and then propyl, then ketone. And that's okay. If you can do the common name, that's fine on a quiz or a test. We might have you do either one. This one's a little bit different. We could call that dimethyl ketone. That has a common name, acetone. We've been talking about that. That's a common name you'll need to know. We wouldn't call that 2-propanone. That would be a pretty complicated IUPAC name. If we said 2-propanone, you could figure it out, but any chemist calling that material will call it acetone. Here's one. I've actually used this word before when we were talking about Grignard reactions. This is methyl vinyl ketone, or MVK. Okay, and that's how a lot of chemists refer to that. And what do you mean there? Methyl vinyl ketone. They're alphabetized. Here's your methyl group, and here's your vinyl group on the ketones. So MVK is okay, that name. How about this one? Benzene and a methyl. Let's see, what is that? Is that benzyl methyl ketone? No, that's incorrect. Remember, a benzyl name refers to 7 carbons, whatever's on there. So that's incorrect. Well, in fact, this is a common name for one we already know, right? This is acetophenone. Okay. Back to chapter 19, I think. But you can use the alkyl name here, but just use it correctly. So what would you call this? Methyl, and then phenyl. That would be the prefix name for a benzene, right? That group's a phenyl group. And M comes before P in the alphabet, and then ketone. Okay. And that would be the name there for that. Okay, good. Yeah, and we'll keep those relatively simple. You should be able to figure those out, okay, with relative simple examples. Okay, how about a little bit on spectroscopy and the properties here. Let's look at the IR. Now, that's a while ago. That's chapter, 13, I think, back in 351. And the IR stretch here is at 1,600 inverse centimeters. And that's the carbon-carbon stretch for a double bond, okay? Remember, we talked about stretches, and that's deforming the bond length, oscillating the bond length, compressing it and elongating it. And we also talked about bending angles. Okay, and that's where we have 3 atoms involved when we're changing the theta angle between there. But here we're just, got that motion going on. Carbonyls, ketones, whatever, are at 1,700. You already know that too. 1720, 1750, sometimes they're a little bit lower than that. We need to say something about that. But the first thing to notice here, you're at a higher frequency here, okay? Which means what? That's a stronger bond, a carbonyl bond. Carbon-oxygen double bond is a stronger bond than a carbon-carbon double bond. Why? Well, you have the electronegativity here, okay? A bigger atom, the lone pairs here, and the better resonance here between the two if what? They're different polarity, okay? Whereas here they're the same polarity, and yeah, it's still, oscillates pretty high frequency, but this is a higher frequency, okay? So the carbonyl is a little bit up there. What about this? You have an amide bond here. This drops down to 1630. Now, we'll talk about amides later on, but in here we're referring to the carbon-oxygen stretch, okay, still. And if we have this here, we have the extra resonance there that really pushes that over. And then we have lower bond order here, which goes to a lower frequency, 1620, okay. Now, there's another thing about aldehydes, a little bit different, and that's due to this CH stretch, which is right here, and that's at 2800, okay? And that's quite a bit lower than a normal carbon-hydrogen bond stretch, okay? Or certainly an oxygen-hydrogen stretch. But why is that? Well, it's because of this partial plus charge there, making it easier to stretch that bond, okay? Let's look at an enone in the IR. So an enone here is also at a lower frequency, 1680. Well, why is that? Let's see what the resonance structure would look like. We looked at this when we talked about cuprates, right? You have this enolate type resonance structure with a plus charge here. And what's that do to the bond order? Here, this number again is for the CO stretch. And yeah, it's a lot lower than a typical ketone, okay, due to that resonance effect there. Let's look at the NMR just briefly here. So at least be aware of those things. That'll help you out in 353 with Dr. Bronson. He'll review a lot of those things, but I like to show a little bit as it relates to structure right now. So proton NMR, let's look at this. So we're talking the alpha position to an aldehyde or ketone, or ester or amide or anything alpha to a carbonyl. Where does this come in the proton NMR? What's its shift, its delta value? Yeah, it's about 2.4 ppm, okay? And what? That's different than an alkane here. If you don't have this carbonyl, where do these alkyl hydrogens come? Yeah, they're about 1 ppm, okay? Why is this? Well, they're a little bit closer to this electronegative group with a partial plus charge there, right? And this partial plus charge shifts this to a further downfield position. It's a little bit harder. It takes more energy to do this. We say these are more exposed to the external magnetic field and they're de-shielded, okay? And that de-shielding means the large external magnetic field is a little bit stronger due to the pulling out of the electron density by the electronegative group. Things that are more electron rich are more shielded. Things that are a little more electron deficient are more de-shielded, okay, due to the exposure to the magnetic field. What about this one? It's an aldehyde, now right on the carbonyl. Where's that shift? Yeah, that's about 9 to 10 ppm. And why is that? Well, it's right on a positive carbon, right? It's a lot closer to the more positive carbon. So yeah, these are around 2.5. This is up here around 9 or 10 for an aldehyde. Yeah, that's probably all we need to say there. Yeah, if anything else comes up, I might throw that in later. But let's review right now, the last little bit here. We'll start the reactions. Well, maybe we'll start the cyanohydrin here today. We'll see how we're doing on time. I think we're okay. We got plenty of time there. Let's review preparation of aldehydes and ketones. So here's the first one. And again, PCC, primary alcohol's got to be primary in order to go to the aldehyde, right? So structurally, make sure you understand that and the reagent PCC, pyridinium chlorochromate. Let's see. we can also make them from esters using what? Diol. Diol will give the same aldehyde in this case, but from the higher oxidized thing, right? The ester in this case. One equivalent diol will stop at the aldehyde, okay? If we had LAH here, it would go to the primary alcohol, okay? So we're reviewing ways of preparing these. We can also prepare it from the acid chloride, and that's using the tri-TB-toxy aluminum hydride lithium salt. Yeah, and that's, 3 TB-toxy groups on aluminum and a hydrogen. That makes the aluminate species negatively charged. The lithium is the counter cation here, and with an acid chloride now also goes to the aldehyde product. Okay. So this is another half reduction. Don't mix these things up. Don't use the tri-TB-toxy aluminate with the ester, and don't use diol with the acid chloride. Those actually are not very efficient reactions. The diol is actually very fine-tuned to an ester, and as well the acid chloride with the tri-TB-toxy. Okay, so limit that to the ones you need there. Let's jog your memory a little bit here. Let's do a hydroboration of a terminal alkyne. Okay, treat with borane, and then treat with peroxide and base. And you're in water here. What do you get? Yeah, you get an aldehyde. Which aldehyde in this case? I'm not meaning to trick you. How many carbons do we have here? 1, 2, 3, 4. So yeah, we're going to have that 4-carbon aldehyde right there. And that's because we do the anti-Markovnikov hydroboration, right? Let's maybe show you a little bit about the mechanism here. Remember that kind of thing? The borane in the empty orbital is actually the electrophile. It's going on the end. It's actually the same mechanism as Markovnikov addition. It's a different electrophile now. And then we oxidize the vinyl alcohol, and then that alcohol tautomerizes to the aldehyde. And we'll review that later when we get to enols and enolates. But that's another way to form aldehydes. Let's see, for ketones, we can take an acid chloride and react it with a cuprate reagent. So that's diethyl aluminum cuprate with an acid chloride. And don't forget about that reaction. We can put that ethyl group in place of the chloride there on the acid chloride to make that. And why does this work? Well, the cuprate is not very reactive. It reacts just once here. Draw the tetrahedral intermediate. The chloride just comes back down. And then ketones and aldehydes are inert to simple cuprate reagents. Okay, they stop at that point. So again, it's kind of matched to the acid chloride. It stops at the ketone. It's a way to make ketones. Now let's see. We can take terminal alkyne and let's do Markovnikov hydration now. So sulfuric acid, water, and sometimes we add mercury sulfate. A lot of times you don't need the mercury sulfate, but this will allow for hydration in a Markovnikov sense. The electrophile is now the proton. It goes on the end. You form the alcohol on the internal carbon, tautomerize again, and now you get, instead of the aldehyde, you get the ketone. Okay, so we know a lot of different ways of how to make aldehydes and ketones. Speaking of ketones, you should remember all the, Friedel-Crafts electrophilic aromatic substitution reactions. Those Friedel-Crafts reactions also let you make all sorts of aromatic ketones, right? With any R group there. So don't forget about those. I won't review those explicitly, but yeah, that's what they would look like there. All right, let's review the reactions here now. And I've already summarized them to some extent, but I like to compare these additions now to carbonyls to additions we've done previously with alkenes. So let me be very brief about this. So here's typical alkene addition, right? And water, acid here going to the alcohol, right? And here we had, carbocation and then attack of water there. Well, let's think about this now. Here we're going to be doing addition is the same thing when we do the hydrate reaction. So we're going to be protonating again, right? And then from there, it's very similar, right? Here we have the resonance stabilized carbocation, and then the nucleophile, the water, going on there. Then we're going to have to lose a proton there or whatever, but that's the hydrate. That's one of the key reactions here in 21. But notice the similarity. Here we're protonating the pi bond, just like here, but we're protonating on oxygen, right, to give more nucleophilic attack at that spot. That's the key thing here. You can also compare this to strong nucleophiles. What if we're going to add a charged nucleophile to an alkene? Well, if it's a simple alkene, we can't really do that because there's nothing here to stabilize that new negative charge there. But if we're talking about a carbonyl here, we can think about charged nucleophiles doing this type of addition. So they're similar in additions to alkenes, but different in a way, okay? And we'll pick it up there right for next time. We'll start, of course, with the cyanohydrin reaction. Then we'll get into the Wittig reaction, the imine, the enamines. Make sure you're reading ahead. These 6 reactions will be somewhat difficult to keep track of, but they're all the same thing. New nucleophiles adding to aldehydes and ketones. And we'll stay limited to aldehydes and ketones. That'll help keep us a little bit more focused in this chapter. Anyway, we'll get into those new reactions for chapter 21 next time, and we'll see you then. Thank you.